Hello, we are Space Concordia, a student society dedicated to the education of space engineering in Montreal, Canada. As the robotics division, we champion rover technology and co-organize events like the Quebec Rover Challenge. We are proud to present our rover for the 2026 season, Deimos. Deimos is built off of our old Series rover frame with a complete overhaul of our electrical and software packages.
Deimos optimizes our tried and tested six-wheeled triple rocker architecture for improved weight and cost efficiency. A T-slot chassis protects our protocase electronics enclosure while serving as a mounting surface for peripherals with the front reserved for mission-specific modules. The enclosure is fitted with IP67 modular plates to safely support I/O with the onboard computer and power system.
Deimos features new fully TPU airless wheels, significantly reducing mass and cost from previous iterations. At 38% weight savings, the wheels are optimized for tank drive and utilize 63 Nm of torque, generated from their encased motors. Paired with our bogies, the tires are capable of crawling over obstacles of up to 30 centimeters. The new design simplifies tire changing to only a few screws. This enables pilots to rapidly reconfigure or repair the set of tires between missions, like optimizing for crawling during the delivery mission or precision during the equipment servicing.
Deimos hosts a completely new electrical system with reliable power distribution and a node-based network centrally controlled by our Jetson Orin. Returning are our 4-cell lithium-ion batteries, which can span multiple missions. Power flows through an IP67 kill switch built directly into the enclosure and is distributed along 3 rails to our arm, wheels, and our auxiliary sub-networks. The CAN network distributes our hardware functionality and returns telemetry of our power management, arm, wheels, and lights to a single bus with 500 kilobits per second throughput. Integrated into this system are custom De Bruyn and Hall effect arm joint encoders to enable inverse kinematics. Chassis temperature readings are used to control 3 cooling fans to fight intense heat, with a third fan cooling the Jetson directly.
Deimos can communicate over the 5.8 GHz and 900 MHz bands for superior video throughput and operation during the equipment servicing mission while remaining capable at 2 kilometers. Pilots can choose from between 4 IMX387 cameras with bespoke video encoding that are complemented by legacy USB cameras. To complement our tested DualShock controller, a 3-axis joystick has been included for precision arm control and backup teleoperation.
Deimos follows a NAV2 autonomy stack that is tested in our custom gazebo simulation environment before deployment. Movements are governed by a custom behavior tree centered around point-to-point GNSS. Differential GNSS, wheel odometry, and 4 onboard IMUs feed Deimos' localization and state estimation using an extended Kalman filter-based sensor fusion from the robot localization package. This allows for the SMAC planner to create an accurate path to be smoothly executed by the DWB controller. Deimos' surroundings are evaluated in a cost map using data from our new vision module sporting an oak depth camera and a 360-degree water-cooled LiDAR. Deimos can interpret Aruco tags and objects using a newly trained YOLO V8 model and the ROS Aruco OpenCV package.
Deimos utilizes our custom cyclodal arm, returning with a new 6th axis facilitating complete 3D space control in both forward and inverse kinematics. New aluminum-bonded carbon fiber tubes, hard stops, and sleeved cabling create a superior strength-to-weight advantage during the delivery missions, while our compliant servo-based gripper can interact with all elements of the equipped servicing mission, including joysticks, keyboards, and USBs. ARM control utilizes the MoveIt2 libraries and ROS2 control framework, allowing pilots to switch seamlessly between forward and inverse kinematics. A USB ARM camera and ARVIS simulation provides the pilots with a gripper view and ARM telemetry. To facilitate autonomous typing, the gripper camera can also track keyboard elements using YOLO V8.
In the science mission, sites are first evaluated using the panoramic camera tower and an external microscope to assess the stratigraphic and microscopic profile of the sites respectively. For analysis, Deimos reuses Ceres' science payload module which deploys from the front of the rover. A subsurface sample may be collected and stored by a custom sleeve drill, where collection windows are revealed at 10 cm depth to minimize contamination. Surface samples are collected into 3 sealed caches with a force to assess dry mass. Hydraulic lines introduce PBS solution in a sample, then deposit saturated solution into one of 3 triplicates in our carousel for spectrographic analysis. Cuvettes are pre-filled with a pH assay to assess habitability, as well as a resizurin and flavin mononucleotide assay to detect metabolic activity through reduction and electron transfer reactions respectively. The wavelength-specific absorbance shifts will be compared against control to assess life presence in the collected samples.
Ares is a lightweight carbon fiber drone equipped with dual camera analog VTX systems for both bird's eye and FPV perspective. It hosts a radio repeater to negate communication losses from non-line of sight operations during the delivery mission.